So this B model is actually about classical and quantum aspects of Calabi Yau geometry. From the first lecture, like you have seen how this is related to string theory, to string field theory, and things like that. So now I'm going to explain a little bit about some basic constructions, facts, and on Calabi Yau geometry that will be used extensively later. So to set things up, like I'm gonna work with like a complex manifold X. With complex dimension D. And I will always use this notion like Tx to be like holomorphic tangent bundle. And so let me first explain the kind of object that I write from the string field in the B model. That's so-called polyvector fields. And in particular, in this case, the main object is the following. Like, let's call this one ij polyvector field, poly ij. It's given by like 0j forms valued in this i's exterior product of the holomorphic tangent bundle. And that's going to be called an ij polyvector field. And this will be the main player in this game. And we will just write sometimes for simplicity this poly X to be all of them, direct sum. Okay, you can describe this one locally in terms of like holomorphic coordinates. So locally, a main element like say mu in this poly ij we can write something like this, like sum over indexes. So here, this capital I and capital J are multi-indexes. Let's say it's I something like with I indexes like K1 to Ki, and J, let's say S1 to Sj, like multi-indexes. And I write this one as a simplified notion for example, like dz bar capital J. This really means like if you with this multi-index, like dz bar K1 wedge. Oh, this for J, so it's like S1 to Sj. And for this this direction, like a vector field, like dzi really means dz K1 wedge dz Ki. So that's my notation for this polyvector field. And it looks like at this moment it's very similar to differential forms. Like we know, like if you work with differential forms on a complex manifold, you have like 0,1 forms and 1,0 forms. It's like an exterior product, and they commute in such a way. Now we basically turn this 1,0 form into 1,0 vector, and this is like called polyvector. There's some essential difference between differential forms and polyvector fields. I will explain along the way, and in particular about this Lie structure. And also, by this exterior product, when I write tensor like mu ij, this one is antisymmetric as a tensor for this multi-index. For example, it's like this guy, smooth, and skew symmetric. For index in I and in J. Okay, that's how you can describe such an object explicitly. Okay, now.
So the cohomology polyvector field is partial homology.
Partial cohomology. Yeah. Yes. Yeah, this is like a way if you want to formulate everything in terms of categories, and that's where you should start with. Yes. Also, as like Phil explained in his talk. Yeah. Let's stay in this purely geometric setup. I also want to simplify all the discussions. So, all this guy, there's a natural product. Just a wedge product, as what you play with like differential form. Similarly for polyvector fields, and suppose you have like poly I1 J1 and poly I2 J2. You can just take the wedge product. This is the wedge to poly I1 plus I2, J1 plus J2. Naturally. And this becomes algebra. And this one also is a bigraded. So you see like there are two indexes like I and J. It's bigraded complex. So bigraded. And like for simplicity, we're going to associate a total degree for some computations. So we associate the total degree is like I plus J. Okay. This is, you can do some other choices like J minus I, something like that. But this is the one that we're gonna use. Okay. Now, out of this data, you see like this object, this polyvector field with the wedge product. This becomes it's a graded commutative algebra. Means like if you multiply object here, let's say alpha wedge beta, the same thing as beta wedge alpha up to the standard Koszul sign. Okay, so that's almost by definition like of the wedge product. Now we have this. Now we have these differential operators like d bar and d operator acting on differential forms. We can translate them to the polyvector fields. The first one, the d bar operator. This bar operator has degree 1. It is very simple, but it's actually useful to remember these degrees for all the operations that arises. So this d-bar operator increased the bool index degree by 1. And then we also know like this is compatible with this algebraic structure. So this is actually a derivation and satisfy the Leibniz rule. Created Leibniz rule. It's like if you calculate the d-bar of the wedge of two objects, the same thing as what you do for differential forms. Essentially, yeah, this nothing changes. So, in particular for like for students, like if you haven't seen this before, like this is if you incorporate everything into this gradients, like this degree, causal science, then it's just a standard like Leibniz rule. Okay, and that's the object we're going to play. So far, this construction works for any kind of complex manifold. No Calabi Yau yet. Now we're going to incorporate Calabi Yau data. And there are many different definitions for Calabi Yau manifold. And so we're going to fix a particular one we're going to use. We need this Calabi Yau volume form. That's what I mean by Calabi Yau in this case. The Calabi Yau for me in this mini course is a pair. Where this X is a complex manifold, and omega X is a nowhere vanishing holomorphic volume form. Okay, so not all complex manifolds admit such a structure. So this one actually put some constraint on the topology. But that's going to be the object we're going to play with. Now, in local coordinate, such a Calabi Yau volume form, this holomorphic volume form, like say in local holomorphic coordinate, like say Z1 essential. So if let's assume our dimension is D, so locally you're going to write this volume form as phi Z dt1 wedge. So it's really a top form, like holomorphic top form. And this one is holomorphic and nowhere vanishing. Yeah, that's the date. That's how we describe this one explicitly.
So you don't require companions. You don't require companions.
I don't require companions, yeah, because I need this data for different purpose. For example, I think in the first half of the lecture we will focus on compact manifold, but later you can generate this one to on non-compact. You can turn on superpotential for Lagrange model, and you can also you can look at something by compactify the space and to get some singularity along the boundary and things like that. But let's say in this way.
If you turn on a holomorphic function, is it equivalent to multiplying the omega to e to the function?
Equivalent to what? To
So you change omega
no.
by multiply e to the w.
Not quite true, but it's but you can do a twisting in such a way. So the differential is like, let me say this the operator is different. So because it depends on you want to do this complex analytically or algebraically. So this operation, if you turn on this superpotential, it's not the same thing as like Yau conjugated by this object. It's not true. Now you can say, okay, well, let's turn on this another operator D, and do twisting, and then combine with like cyclic operator. Then you can do this game by twisting. But it's not e to t; it's actually t e to the t, f over descendant. Then it's true. Yeah.
Then it's true. It's equivalent.
You can the complex. You can tune this complex, but it's not. How can I say this one? The field theory is not equivalent. But this equivalent up to, say, if you look at equation motion, this is a particular solution of the Markov equation. So this is equivalent in the following sense. If you start with the original theory, you have kind of Markov equation, things like that, and this is a particular solution of the Markov equation, then this is the twist of the original theory. That is equivalent. So it's the equivalent to the twist of the original theory, but specified at this point. It's a more precise way of saying this. Does it make sense, or?
That twist theory is equivalent to one of the superpotential.
The twisted theory is with equivalent to this one. Yes, yes. But it's not the equivalent to the original theory. Yeah.
So that is the potential in the
yeah.
to bring about doing this.
The twist, yes.
So twist means evolve past gradual.
Twist means like specify. Oh, the twist have different perspective. The twist I mentioned is like specify to a solution of Markov equation. Yeah. Now, one of the things we're gonna use for this volume form is to give additional structure on polyvector fields as follows. So this Calabi Yau form induces a linear isomorphism by contracting with the volume form. You can identify IJ polyvector field with like differential form of type d minus ij by sending a polyvector field to this object contracting with the volume form. And that's the very natural thing to do because this one contains like a D, like the volume form. So if you contract with like a polyvectors, you end up with a fewer forms, and that's so you contract I index, you end up with like n minus I indexes. Now, with this, and because this is like a volume form, this is a linear isomorphism. So you can transfer all the data that you have on differential forms back to the polyvector fields. And then the particular object we were going to play with is the so-called divergence operator. So we know, like in geometry, whenever you have a volume form, you can talk about divergence operator. The divergence operator, you're going to write such a way. It decreases the I index by 1, the divergence operator. With respect to the volume form. And more precisely, it can be obtained as the following diagram. Say, you identify this polyvector field with differential forms. Now, on differential forms, you can take the holomorphic theorem. So you get d minus I plus 1 j. And then you identify this one back to polyvector field. And this diagram gives you this operator. And that's how this is defined. Of course, this one depends on the choice of the volume form. And that's why it's a divergence associated to the volume form. Okay, so somehow later we actually, to simplify the notation, I will not write this down explicitly in terms of this omega. I'm going to write we're going to just write this divergence just like a d. It's a little bit confusing for this one because it really depends on the choice of volume form, but it saves the chalk. So let's do this. So what we really mean by this del operator means like if you act, this one acts on differential forms, means like holomorphic theorem on forms. And if I say apply this one to polyvector field, really means divergence operator. Okay, just to confuse ourselves in a little bit. Yeah. Okay. Any questions so far?
So if you have a holomorphic synthetic form, do you have something along the same line? They have all these similar things.
I don't know. Maybe.
Maybe omega to any power.
Yeah. Holomorphic form. You probably get some refinement coming from this implied structure. Yeah. That might be interesting. Yeah, I have no idea. Yeah. Good point. Yeah. So the seems looks like this structure looks simple, but actually this underlies a key idea in quantum field theory. Somehow, the way to do quantization basically is to understand volume in quantum physics, and understand volume basically is to understand this operator. So this operator in physics is called this is like geometrically divergence, but in physics it's called the BV operator. So this is actually a very important operator. So the way it is called BV is the following: like this object, like holomorphic theorem on differential forms, it's a derivation. It satisfies the Leibniz rule and things like that. But on polyvector field, with respect to the wedge product on polyvector field, it's not a derivation. So this guy is not a derivation. So it doesn't satisfy the Leibniz rule. So now we can look at how not, or what is the failure of this one being a derivation. So the failure let's say just a failure is described by, so just write down the Leibniz rule and look at the anomaly. It's given by, say, alpha beta. It's defined to be the failure. Okay, the right hand side is about the Leibniz rule. So this bracket is 0 even only if the right-hand side, the operator satisfies the Leibniz rule. But this one is not. So this one actually is non-trivial. And this bracket is something that we actually know in geometry. And this bracket is related to so-called Skelton-Nearest bracket, but not precisely the same. It differs a little bit. You know, like in differential geometry, we know we have a generalization of the Lie bracket on vector fields to polyvector fields. So it's called a Skelton-Nearest bracket. They're almost the same, but up to a sign. Precisely, it's given by the following: the geometric bracket equals this bracket. Let's call this one BV bracket, blah, 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 by this sign. Okay. And this relation, yes, the different names for this one. Sometimes people call this one like Bogomolov-Tien Todorov lemma. And in physics, it's about the BV algebra and things like that for this object.
So does it satisfy the graded Jacobi identity?
Yeah, I'm going to write it, yeah. And the reason for this shifting actually is because this is really a Lie bracket. No, this is a polyvector field. Like you have to shift the degree to obtain the Lie structure. So the vector field is like in our current degree is at degree 1, but as a Lie algebra it sits in degree 0. So if you shift degree by 1, that changes the Lie bracket to this odd Poisson bracket. Yeah.
So the vector field is on degree 0.
Yeah. So somehow you can say this bracket, this BV bracket, is the shifted Lie bracket. And the shifted Lie bracket differs by the Lie bracket by this sign. This is like this sign actually is also standard in this supergeometry. Yeah.
So what is BTT lemma?
Bogomolov-Tien Todorov.
What's the statement?
This equality.
This
This equality?
Yeah.
Downstairs.
no.
This one.
This is the definition.
No.
The statement.
You go to that one. You go to SA.
Yeah, you have to go to Skelton-Nearest bracket. Then this statement is called Bogomolov-Tien Todorov lemma.
Okay, I see.
Yeah. Okay. Now, yes, Conan just mentioned, this one satisfies a bunch of properties. First, this bracket. I'm gonna call this one BV bracket anyway. So this bracket, odd Poisson bracket. First one, if you look at how it acts on, suppose you have like a I1, J1 polyvector, I2, J2 polyvector. You take the bracket, you end up with something here, poly I1 plus I2 minus 1, J1 plus J2. And one of the key points here is the following, like the Skelton-Nearest bracket is defined for any kind of manifold. It has nothing to do with the volume form. And the same thing here, that this bracket is defined, actually intrinsically defined geometrically, doesn't depend on the choice of volume form. It's actually intrinsically defined. or on this B-way operator. So, although they are related in such a way, but the bracket on the left-hand side is actually quite geometric. And sometimes, just a remark, sometimes if you look at some physics literature, the lifting of this bracket to this B-way operator or this kind of a Calabi Yau, the volume form, is about this B-way quantization process. We'll say a few words about this idea later when we discuss the quantum beam model. But it's not on this geometric model, it's on another one. And a bunch of properties, I just list these properties, and it's an exercise for you to do. I mean, afternoon is an exercise session or something like that. you can do this exercise. For example, you have this graded symmetry. So, if you look at the bracket of f and beta, if you switch the order, it's like looks like a graded commutative. Yeah, this is graded commutative in just a shifted sense. If you go back to the original degree for Lie structure, then you get a school symmetric property. Then you have the Leibniz relation. So, for example, if you calculate the bracket of alpha with beta wedge gamma, it's just like the Leibniz rule. So, if alpha bracket beta wedge gamma, then the other way you will switch the order, it becomes something like a beta gamma and also this Jacobi identity is in a graded sense. Yeah, because I'm going to use this one extensively later, so let me list these properties. And for you to do, I mean, if you haven't seen this before, the equals minus. Yeah, I want to be very precise. I think the signs are correct. If you find it not, let me know. And this is an example of so-called differential Gansen-Haber B-way algebra. So this is an example, like just a remark. This data is a fundamental example. This is an example of about this has origin from this so-called Gansen-Haber bracket. If you work with like Hochschild cochains, it's a fundamental. Example of so-called differential Gansen-Haber B-way algebra. And exists in a large class of examples. Okay. The last data I need before we move on to discuss something about this moduli is the following. This is also a crucial object. It's about the trace. So on Calabi Yau, I can integrate. So now I can work with like compact manifold, or I can work with polyvector field with compact support and things like that. But anyway, we're going to define this trace. On polyvector field by integrating, by doing integration against the holomorphic volume form. So the precise definition is the following. So first you contract with the holomorphic volume form, and get a differential form, and then match with this guy. And then if you compare with type, this is only non-trivial for the top polyvector. So trace is only non-trivial. So by comparing with type. And later I'm going to use this trace to describe a so-called a version of so-called higher residue and this symplectic structure on this field space.
Think about this structure as given the algebra, and then you want to find theories so that it's monotonically true. Take hold of saying that there's a theory so that this is monotonically true.
I don't know, like, but this, but that's just algebra, right? This is that's exactly this algebra. Yeah.
So
yeah.
we've given the algebra first. Right?
But why it's trivial? It's not completely trivial.
Because if D of something is in the kernel, then the bracket is also D of something.
Yeah. Yes. So yeah, I would say this. Exactly. It's about not. You have to add into one more condition. It's about Hodge-Durham degeneration, or this D bar lemma things. Then this is almost like trivial. But then D just like applied to kernel del is like a del exact, which is true. The bracket on this one is trivial. There's a trivial bracket on this object on this Calabi Yau like volume preserving vector field. That's true. Yeah. That's true. Yeah. It's like a homotopic version of this. Yeah. Okay. The last thing I want to mention, actually, also this exercise, to show this compatibility of this trace map with two differentials. One is d bar and one is del. Actually it's a school metric for d bar and just metric for divergence. It's actually different. So, and the difference is important. We're going to see later, like how this is related when we write down so-called higher residue parents, and this is going to be crucial property. So trace, the d bar is an exclusive metric with respect to the trace pairing. If you look at the divergence operator, it's a symmetric in a way. Yeah, so differ by one sign. Okay, this is an exercise. Now, with this preparation, we're going to use this one to describe the first, a local structure for the moduli space. And this is basically what Colin is mentioned. I'm going to make this one precise. Okay, so for simplicity, I mean, to illustrate the basic idea, we're going to work with compact Kähler. Calabi Yau. Let's start with compact Kähler first, and then we will see what's the role of Calabi Yau that enters in this game. So the deformation space of complex structure of X is locally described by the following. And you can do this one algebraically, or you can do this one like complex analytically. And in terms of differential equations, this local moduli is given by, this deformation is given by an element of this poly 1, 1. And as a local moduli, we specified the norm to be small. If epsilon is small enough. And solving this Maury-Cardan equation, and with a gauge condition, the standard Coulomb-Spencer theory. Okay, this is the equation described the moduli space locally. And this is the equation described the deformation of complex structure. This fixed the gauge, it fixed the automorphism. So this is a gauge fixing condition. Okay. Now, the first statement is the following, like, assume, like Bogomolov, Kn Todorov, like for compact Taylor Calabi Yau, this moduli space actually is smooth. Locally, it's actually smooth, locally smooth. And we know from standard Coulomb-Spencer theory the dimension of this moduli space is actually complex dimension, H1, the cohomology. So it's really nice actually. Whenever you have Calabi Yau, the local moduli is smooth. And you can actually say a bit more about this. So in general, I'll tell you how to prove it, like in 2 lines. So, but in general, we can consider extended moduli space. Extended moduli space. Let's call this one M by solving the same equation, but we can enlarge the elements here to include basically to include all the polyvector fields. So by solving this one, and modular gauge, or you can do gauge fixing for any type. All types. This is sometimes called an extended moduli space. Okay, so you can view this one as actually a slice or submanifold of this extended moduli space. Yes.
You're defining it starting from one particular solution. starting from one particular.
Yes.
So you need an intrinsic definition.
Yes, this is like a, yeah, this is like a, that's right, yeah. And you know how to deal with this one. But I modular gauge or, that's right, yeah. That's all the issues in this modular problem. Now, the theorem of Barnikov-Kontsevich basically extends that result by saying that the extended moduli is also smooth. Okay, and actually it comes from a purely algebraic fact, and the consequence of algebraic fact about this BV algebra or this BDT lemma, and also a version of Dirichlet lemma. So, but let's prove it. It's actually very illustrating to see the Calabi Yau geometry, and we're going to use this one later to do some other constructions. So the proof goes as follows. So let's consider first all the divergence-free subspace. And then actually you find that this BTP lemma or this BV algebra says the following. This is exactly what Conan said. So given two elements of this divergence-free vector field, if you calculate the bracket, this BV bracket, then you see this BV relation or this BTT lemma. Because alpha beta, they are somehow they are by assumption a divergence free. So this term goes away, this term goes away, and this one actually is a del exact. So we find that the BV bracket as a bracket on the divergence-free vector field leads to something like a homotopically trivial. It's like a del exact. Okay, that's a subspace here. And this is going to be the crucial statement for showing this smoothness of a modular space. So how this works. So here's the picture. Now, what this one says in particular is the following. Originally, we have actually we have shifted differential gradient Lie algebra by this polyvector field, and we want to solve equations with Markov equations associated to this shifted differential gradient Lie algebra. So this original complex, this is a DGLA, or some shifted version. So let me not distinguish this notion. We want to write down a Markov equation here. I want to solve equations up to gauge. Now, this one says the following: we have actually a subspace. Let's call this embedding J by this divergence-free vector field, and del bar and the bracket. First of all, this bracket applied to the kernel del, a divergence-free vector field, is also divergence-free. So this is really a sub DGLA, differential Lie algebra, and this is a subspace. But this morphism is actually a map of differential Lie algebra. Okay, then one of the crucial properties about this map is like this is a so-called quasi-isomorphism. So if you look at the level of cohomology, so suppose we'll let this H to be harmonic polyvector fields. Then by this Kähler property, we know we can calculate this harmonic by either del bar cohomology or del cohomology, things like that. So this guy is isomorphic to kernel del mod. This guy is also isomorphic to kernel del bar mod del bar exact by Kähler property. Okay, so this will in particular implies that if you calculate the d-bar cohomology of this space, this will actually be a cohomology level will be the same. It's called quasi-isomorphic. But let me put this one put one step further, like to get more structure. So let's call this one this harmonic projection to be pi. Then what we find is actually the following. Right? First, by Dilibar-Lammer, this del bar. Oh, by the way, this is subcomplexes by Dilibar-Lammer, but let me write it here. So you actually also apply this one to get something exact. This is what you find. Then you see like this map actually projects the whole DGLA to even something simpler. So if you find the morphism like kernel del and the del bar and the bracket, this differential Lie algebra, you can map this one to cohomology, harmonic, and with zero differential. And you see like this property just tells like if you look at the commutator, the bracket, and the image is actually del exact. So it means like if you look at the bracket at the cohomology level, it's actually also zero. So this one is the map of a DGA as well. It's compatible with differential and compatible with bracket. But this DGA is extremely simple. So now here's the picture. We have kernel del bar at the bracket. This is my one of the DGLA describing like a volume preserving vector field, divergence free. Then subspace of the original deformation problem. It's my J. And also project to another one, harmonic, and 0 and 0. And you can check, just check. Both map are quasi-isomorphisms. So both and J and pi are quasi-isomorphisms. Means that if you look at the differential and compute the cohomology of the differential, it's isomorphic. So then by some abstract nonsense, we know like whenever you have a map of differential Lie algebra, which is quasi-isomorphic, then you can induce the isomorphism on the moduli space. Basically, if you solve Maury-Colin equation modular gauge, induce the same functor, isomorphic functor. So if you solve equations, you solve this equation here, the same thing as solving equations here, modular gauge, the same thing as solving equation here. But the equation here is trivial. So they have the implies that these two have the same moduli. And this moduli is just the H itself. So this implies that the modular space actually is isomorphic to H itself. And that's the end of the proof. And that's the proof by Barnikov-Kontsevich.
But where is this solving for small radius? This is solved for
Locally.
Where's the local condition?
Oh yeah.
This seems to be solving for all.
No, this equivalence is for formal equivalence.
So
Yeah.
So it's very far.
It's formal equivalence. It's a local germ. Yeah. Yeah.
Where do you expect that the normal field is less than using?
You have to work with locally. It's a small piece of them. You have a big modular space, but I only work with this is a big modular space. I was thinking about this local behavior.
Yeah.
Yeah. So the large behavior is different. This is analytic, but the statement about equivalence is formal. Yeah.
Is this like a Lagrangian correspondence?
No. Why is it Lagrangian? you want Lagrangian correspondence for everything. But actually, the the next lecture I will be starting to talk about these Lagrangians, and you will see how Lagrangian leads to it's different Lagrangian, yes, but it's a Lagrangian. It's again Lagrangian, yeah. And then this and the mass equation is also about this. As I mentioned, like Hamilton-Jacobi for Lagrangian manifold. Okay, so.
This notion about Calabi Yau, just one relation for the morphic order one, is it the shifted versions?
For.
So the shifted Calabi Yau stack?
Maybe, I don't know.
So that was a shift?
Maybe, I have no idea. I'm sure this is extended in a lot of different contexts, but I'm not following them. But I think so, but I cannot tell the reference. Okay, I think I'm gonna stop here for today. Yeah.